Okay, so last week we were working with exponential functions, evaluating them, graphing them, things like that. So today we'll be doing a little more with it, but this will have a more real world application to it. So today we'll be learning about exponential growth and decay. So first things first, in exponential growth, what do you think would happen in a function like that, Trey?
We're gonna see a line of
We're gonna get an answer that's bigger than what we start with, right? Okay, and then what do you think is gonna happen in decay?
lower.
It's gonna be lower than what we start with, exactly. So, first things, in the exponential growth and decay formulas, which are, right, let's not do that. There we go, there's exponential growth and there's exponential decay. The variables in it, y is our final amount, so whatever we might be given the final amount, something like that. A is our original amount. R is the rate of growth or decay, so either it's going to be growing at a certain rate or going to be decaying at a certain rate, and it's written as a decimal. And then T is time. So, first things first, if you see the two formulas for exponential growth and decay, what's one thing that you see that's different between them? Josh?
One is 1 plus r, and the other one's 1 minus r.
Okay, and what do you think that is? Trey?
The rate of change.
Okay. Malcolm, were you going to say something?
Yeah, one's going up and
Okay, so which one's going to be going up?
lower. The
This one? Right, it's 1 plus r, so our rate is, if we're going to be increasing, we have to be something greater than 1. It's greater than its starting point.
Why does it have to be greater than 1? Like, what if I started with -8 and then I went up to -6?
Because it's 1, so a is our original amount, so anything times 1 is an original or itself, right? So to find the amount of increase, if we just multiply it by our rate of change, we would get a number that's smaller than it. So we add that 1 in, so it's our original amount plus its percentage of change. So that's where the 1 plus r comes in. So on that note, what do you think the 1 minus r means?
If it's lower than 1.
It's going to go down at a percent rate, right? All right, so our first little example, it says the population of a city is increasing at a rate of 4% each year. In 2000, there were 236,000 people in the city. So write an exponential growth function to model this situation. So, first things first, what are we being asked to find in that question? Or what is that representing? What is that example asking us to do or describing?
you say it again.
What is the example describing?
Oh, the graph.
How many people are
Population of a city.
Yeah, population of a city. It's describing that it's increasing at 4%. So, given the function that we're going to come up with, whatever amount of time that we plug in, we should be able to estimate what the population will be. So, we have our variables that we need. So, identify our variables. A is 236,000. What does that mean again? What's A?
Your original amount?
Right. The 236,000, that's how many people were in the city in 2000. What's this R equals 0.04? What do you think that represents?
That's the percentage of
Right, so 4% is 0.04 because that's 400ths, that's what 4% means. So we have our growth formula written out right there. Substitute for A and R because those were our two variables that we found. So y equals, A becomes 236,000 times 1 plus 0.04, and that's taken to the t power. Alright, so after that, we just do our order of operations. So the exponential growth function is, we do 1 plus 0.04. Do that, so our formula right there becomes y equals 236,000 times 1.04 to the t power. And we know that it's growth because our rate is greater than 1. So last step, substitute for t. What will we substitute in for t then? If our time is t. Because we're being asked to find the population in 2009, right? So how many years have passed since 2009, right? So right there, it's really hard to see. So it says y equals 236,000. And I'm running out of room. 1.04, just bear with me right now to the 9th. You don't have to write that down. So, what is 1.04 to the 9th power? Someone have their calculator out? Okay, and multiply that by 236,000. Okay, so the last thing of that was 902 or 1.5, right? Can we have a fraction of a person?
No.
No, because we're really talking about population, which involves people, so we should round that up, right? So that's where they get the 335,902. So what is that answer telling us about what we just did?
The population will reach
When?
2009.
9. Right. So in 2009, population will be about 335,900 people. Good work. Now we have exponential decay, so it's kind of the same thing. The only thing that's going to change is our rate that we're multiplying by. So population of a city is decreasing at a rate of 6% each year. In 2000, there were 35,000 people. Write an exponential decay function to model the situation, and then find the population in 2012. So they identify our variables. A is 35,000. How do they get that? Where are they getting that 35,000 from?
35,000
Mm-hmm.
people.
Right. It says right there, in 2000 there were 35,000 people in the city. And then R is our rate, so
6%.
6%, exactly. So we have our basic formula for exponential decay, y equals a times 1 minus r to the t power. So we just substitute in our two variables. 35,000 comes in for a, 0.06 goes in for r. And just do your order of operations. So 1 minus 0.06 becomes 0.94. And since our rate is less than 1, that's how we tell it's exponential decay. So once we have that all figured out, we just substitute in our t value. And what is that going to be?
Difference, like 2000 to 2012, that's 12.
Right, so from 2000 to 2012, how many years is that? 12 years, so that's what we plug in for t. So, if you work that out in your calculator, you don't have to right now, but our answer is going to be 16,657. So, when we were dealing with our first one, it was exponential growth, right? So we got a number that was greater than our starting value. So that makes sense. And then for decay, we started with 35,000 people, and we ended up with a number that's less than that. So that makes sense too. All right. So we have our little example problem. So it says write an exponential growth function to model the situation. Then find the value of the function after the given amount of time. So this first problem is annual sales at a company are $372,000 and increasing at a rate of 5% per year.
So A is 372,000 and R is 5.
What are you doing there, Shamarky?
I took the company where they only said 2,000, and then for the rate is R, which is 5%.
You're identifying your variables, right? That's our first step. Good. So you said A was
372.
372,000, and then R was what?
0.05.
0.05. All right, so those are our two variables. We got that down. Second step, substitute for A and R. So first we have our general formula. Is this going to be exponential growth or decay?
Growth.
Growth?
It says right on the top. For an exponential growth function.
Yeah, it does, doesn't it? So it better be growth, right? So it should be 1 plus R to the T. So we have our two values that we substitute in. All right. Can we leave it like this?
No.
No.
We got one more step, so what do we do?
Parentheses.
We do what's left in the parentheses. So we have y equals 1.05 t. So that's our first step of the problem. Write the exponential growth function to model this situation. We have that all written out. Doesn't look like we can simplify anything else, right? Alrighty then. So, next part is find the value of the function after the given amount of time. And right here it says after 8 years. So what do you think is going to happen?
The T's and E.
Isaac?
We're gonna start put our 8 in for the T.
8 in for T, okay. So you have 372,000. 2,000. Oh, I'm writing too big. Times 1.05 to the 8th. So what is 1.05 to the 8th power?
1.4775454446. I just know that there's
So 1.48.
No.
Do we get a round?
Nope, actually, you can just plug into your calculator 372,000 times 1.05 to the 8th. So what is that?
You just write it down back there.
In times
549,613.25.
Say that again.
5,
549,
6,
240.
6, 1.
61,
3
3,
point
Point.
4251.
okay, that's as far as we can get. So, in this problem, what are we dealing with? Money. So what is our label gonna look like? Or is this our final answer?
That's the
No.
final one. No. 43. Do we need that decimal behind it?
Yeah, you need a decimal,
What's
but,
up behind the decimal?
oh, we're dealing with money, right?
Oh, we're doing, I thought we were doing population.
Yes, Brayden?
So then, wouldn't we round that 5 to the 2, so then, yeah, 549,300, 613 at .43.
Mm-hmm. Dollars, right?
The next question.
Since we're dealing with money, we only round to the hundredths place, right? We only go as far as the hundredths place. So that right there is after 8 years, the company's sales rate is at $549,613.43. Yeah, it'd be real nice to have that much money, isn't it? All right, does anyone have any questions so far about exponential growth before we move on to the decay part? All right. Now, our second problem, or second example, is write an exponential decay function to model the situation. Then find the value of the function after the given amount of time. So, our situation is an internet chat room has 1,200 participants, that's a lot, and is decreasing at a rate of 2% per year. So first things first, what do? A and R, so what's our A?
1,020.
1,200, and R is? 0.02. Okay, did that, so now we substitute our A and R in, right? So we have y equals A times 1. It's going to be plus or minus?
Minus.
Minus because it's in decay, right? So just rewrite it, y equals 1,200. 1 minus 0.02 to the t. Are we done yet?
No, 1,000.
Nope, still got one more thing, or one more step to do, right? So y equals 1,200. 1 minus 0.02 is 0.98.
5. The T-shirt.
That's not.
Okay, so before we move on, we wrote an exponential decay function. Does this look good to everyone?
Yeah.
Our rate is 0.98 because it's decreasing by 2% every year, okay? So after that, our second part of our problem is find the value of the function after the given amount of time.
5 years.
And it says after 5 years, so I'll just rewrite what we got there first. To the t. So what is going to be our t value?
5.
5. So we rewrite it, substituting in 5 for t. It goes right there. So you guys can just plug this whole thing in your calculator. You don't have to do one step at a time.
Oh, everything is going to be 1084.70.956.
Hold on, Shamarky.
What'd you get?
Well, I got 1084.
Okay. Like you said, like 6 something.
6.
Yes, Daddy.
All right. So it looks like everyone's got it. So, JC, what did you get?
The same thing as Cherokee.
And what is that?
1084.
Yeah, 1,085.
Trey?
It's 1,085.
Yeah, he rounded up. You
You
can't
can't
fraction.
What did you get as a decimal answer?
What decimal?
Yeah, what was your decimal answer?
4.704.
0.70 something?
04956.
049. Okay, so what is this internet chat room, or what is our situation describing?
Participants decrease.
Participants in the chat room, right?
0.02.
1085.
So can we have 0.7 of a person,
No.
or 0.7 of a person?
I would choose.
So we round up, right? Because 7/10 is closer to 1, or closer to 5 than it is to 4. So we just rewrite it as. Am I done?
No. Label.
Label. So what would I write?
Participants.
Participants.
I do have a question though.
Yes, Trey.
What if, the person there is like missing a limb?
Is what?
Missing a limb? Like
Trees are part of math.
Well, no, I guess that is because
Stop.
that doesn't
Change, let's go in the hallway and collect them, or are you gonna be done?
Oh my god. That doesn't, alright.
It's not funny.
I'm not laughing.
Okay, so this was an exponential decay function, right? So we started with 1200 and we got 1085. So that's less than what we started with, right? Does that make sense since we're using a decay function? Yep, I hope so. So with that, I'm done with the notes, so you guys can work on your assignment. It's right over there on the board. You guys are free to work.